So we started the topic of root finding last time, and in particular we dealt with one of the, what one could call brute force methods, which is called bisection. The way bisection works is I start graphically. I find the root, or roughly where the root is. So if I have a given function, I can plot it, and I can see if I can find any intersections with line 0, because I'm looking where the 0 and this functions are equal. Okay? And I can see that there is a root here in the neighborhood of 15. So first thing that I need in bisection methods is I need to identify a segment, okay, such that if I look at the lower value of that segment and evaluate function f, I see, for instance, a positive value, and on the other end I see a negative value, or the other way around. Okay? So if I have, for instance, here I have a positive value here and a negative value here. If I actually have that, then I know if the function is continuous that I have to hit a 0 somewhere in between. So now it's just about narrowing down my segment to close proximity of that 0. Okay? Alternative would be, of course, that I actually had a negative value here and a positive on the other end. Either way, the way we mathematically evaluate that is that if this is my xl, this lower root, if this is xl and this is xu, f of xl times f of xu is less than 0. So that means that they have opposing signs. Okay? So basically, that means that I have a root, or maybe 2. If I go very broad, I might have 2 or 3 in there. Okay? I have a root that I can proceed. Now, so here's then the method. So then I'm going to basically half this interval. And out of the 2 halves of the interval, I'm going to pick the one that has the same characteristic. Rather, on one end, I have, if I evaluate f at one end times the other end, it's going to be still less than 0. So in this particular case, let's say they had 12 and 16. If I bisect, this is my new value is 14. If I look at f of 12 times f of 14, that's actually larger than 0 because both values are positive, so that's not the one. I take actually this other segment is my new segment. So my new segment is where I have f of 14 times f of 16 less than 0. And then basically what's going to happen is my new lower value, my new lower bound of the segment becomes 14. So I simply say xl is now 14. And I keep doing that in a while loop, okay, until I reach that segment length is small enough. What I call small enough is up to me. So I can say, oh, I want this root with a precision of 0.001, okay? And basically I keep going until I close into that interval of the root. Okay? So basically this is the algorithm, and we programmed that algorithm as an assignment, which I hope all of you have submitted. Okay. Now we will actually give some alternatives to this method. So bisection is sort of brute force. It's brute force because I'm halving the interval without really consulting the function where this new value should be. So it can actually be quite slow. But there's an alternative to it, which is called false position method, okay, which is actually looking at magnitudes of what is my function when I evaluate it at this lower end of the segment and the upper end of the segment. So basically, I know that my function is some sort of nonlinear function, because otherwise for a linear function I wouldn't have trouble finding a root. So basically I'm just going to say, okay, my function f hits a 0 somewhere here, but I'm going to take a linear approximation to this function and basically say, well, this next point xr is right here, which is the line where the line in between f of xl and f of xu intersects the 0. Okay. So when I evaluate that graphically, I know that these two triangles are similar. So basically f of xl divided by this xr minus xl. So basically this length divided by this length has to be the same as this length divided by this length. And I can actually solve that for my xr. What is my next xr? So this is just trying to pick the value xr in a smarter way and not just bisecting it. And the smarter way says, okay, I'm going to look at the function, linearize it, and pick where it intersects. And I'm hoping that I'm going to pick rather close to the root. Okay. So basically, I'm gonna. This is going to be my new xr. Okay. And one can actually look into that. So bisection is actually essentially guaranteed to converge because I will get closer, but it might be slow. And false position is also guaranteed to converge, but it's hopefully quicker. Now sometimes I might actually hit a problem where it's not, but this is how I'm picking my next interval xr. Okay. So how about you take your bisection.n and modify it to actually, let's call it false position.n. So let's actually program this in and actually see. Now I also want you to evaluate the error. So this is my formula for xr. So this is how I put, so I want you to, I'm gonna write that in. False position dot m, or possibly add it to the same and compute errors similar to that solves the same problem. And also modified both scripts to also compute this relative error so we can actually compare them. So again, main difference is how do I pick this next xr, and in bisection it's just the half point between xu and xl, and in this particular case it's hopefully faster and smarter choice. And I'm gonna walk around and help. So start working from your bisection.n. I have a computer to work on. Pick somebody. You can also work on the paper. That's a better practice for test anyway. If you need a computer, you can also get one. So it's up to you. You can work on the paper. And let us know if you have questions. And if you would write down this formula so I could turn this off and solve it myself. So actually I'm going to write it down. So XR okay. Bless you.
Wow.
Does anybody plot the error for both cases?
I mean, that's not what Jim meant.
How does your Facebook
No, it's something.
You could do that, or you could just do absolute error. So I think the slide suggested absolute error. So yes. Yes. So essentially question was here. What is the error that you would like to plot? If you do, no, it's actually relative error. So yes, so I can plot absolute error or relative error. In this particular case, I'm searching for the root. I don't have it, so I can't measure the error with respect to the true value, okay, the true solution, because I don't have it. Then I'm actually working with the best possible that I have at the moment. And those are my last two approximations. So in this case, it's going to be XU and XL. Okay. So I can actually then report the error as the width of this interval divided by XU. That would be the relative error. Or I can look at the absolute error and just report the width of the interval. Okay. So basically, at each step, here's how I would modify by section. So this is my bisection, which is kind of prettified with all of the comments. But basically, I clear and close everything at the very beginning. And this first part, I'm just plotting my f of x. This is what we were doing last time, just to actually see where it is that I want to zoom in on the root. So I can run that part. Oops, it ran everything. Never mind. So this is first part. This is just plotting my function. And I can actually see that there are 3 roots. Some of you picked this root close to between 4 and 5 last time. That was that polynomial we worked with. Some of you picked the one between 0 and 2, but there is actually another one between -0 and 1. So either way, we're looking for one at a time. So let's say that I'm looking at the one between 0 and 2. That is my initial bracket, so my left point is 0, my upper point, or lower is 0, upper is 2. Okay. And here, let's say that I'm looking at the, so I can modify this to plot a relative error. So relative error is absolute value of divided by XU, assuming XU is different from 0. In this case, it is, so I'm good. Okay. So this is the relative error. And then I can say, okay, while relative error of I is larger than whatever it is that I pick, in this case, it's 5 times 10 to the minus 5. Okay. I want to record this error, so I'm actually adding this iteration counter. And I'm setting my XR to be this value. And I'm storing also XR because I want to plot it for you at the end. So I'm storing sort of the current value of this midpoint. And if my f of XR times f of XL is less than 0, then XU is XR. Otherwise, XL is XR. And my relative error is absolute value divided by XU. There are some other alternatives. I could, in this particular case, because I'm looking for where I have a 0, I could actually look at the absolute value of f of XR because I'm looking for it to be closer and closer to 0. But that kind of depends on function f, so it's typically avoided. And then I found an approximate root, and I can also record how many iterations. And when I'm plotting the results, okay, I've actually here, I was plotting all of this. So this is the function between 0 and 2, and all of these red points is basically where I'm hitting closer and closer to the root. So it kind of ultimately zooms in on this area. And my relative error, let me rerun it. Oops. And I'm hitting, I modified something, and I'm gonna, I need to plot relative error, not error. Okay. So this is the function. This is actually the points as I am evaluating the XR, and this is my relative error going all the way down with the number of iterations. Here I had 17 iterations. How do I modify this code to work with as false position? What do I change? I have this entire code. It's working for bisection. Now I want to do the same measurement for false position. Where do I modify? My XR, and that's pretty much it. So basically, for false position, this becomes XR is equal to XU minus f of XU XL minus XU divided by f of XL I have it from before. I'm going to call it false position 1. And I'm actually going to not clear everything. So here, whoops. So basically the same code will then plot me the error. The log of the error did not go down. So possibly I have a typo I need to fix. But essentially that is the false position. So I'm gonna post these solutions online. Enjoy the spring break.